Thank you for joining, and you probably know me already. My name is Oksana, and I'm a digital library developer here. But before that, I worked in the Data Science Institute. My background is in linguistics, computational linguistics. So today we're going to be talking about linked data. And as I said at the previous workshop, if you were there, it's somehow connected to network analysis, right? Because it's also about representing data in a structured way as a graph. And it is a huge topic. When I was studying here in the first year of my PhD, I had a module, like a whole semester module on linked data. It was a very heavy workload. So we're just going to discuss the basic concepts and just introduce you to them and to the data sets that are available and to the software that is available. But we won't be, this one workshop won't be enough. If you want to dig deeper into the topic, I've provided a reading list at the end of the presentation with more tutorials, documentation, and stuff like that. And I'll share the slides afterwards, again, as usual. So, what is linked data? Come on. Linked data is, as I said, structured data, which is interlinked with other data, so it becomes more discoverable, and you can query it with special semantic queries. Right? It is using the standard web technologies, and it is aimed at computers in the first place rather than humans, right? So it is by definition machine readable structured data that links different items together. Linked data by definition is not open, but you will hear people speaking about linked open data. To be open, it must be publicly available under an open license, as anything open source, right? So the illustration here is a graph, a Wikidata graph of different domains that are colored. So like user-generated stuff is maroon, life sciences related stuff is yellow, and as you can see, they are the thematic communities are linked together tighter than with the rest of the graph. We'll talk about Wikidata later. So how it all started, as I mentioned, linked data uses web technologies. So it all started with the invention of the Wide Web and Tim Berners-Lee. So in 1989, he invented the World Wide Web, and in 1993 it became really publicly available, released into the open domain. In 1994, the World Wide Web Consortium that still exists is founded. It is a regulatory organization that manages all the standards of how basically the web works. And in 1999, he introduced the vision of the next generation of web, so-called semantic web. Or Web 3.0, and the goal of the semantic web in his vision was to make internet data machine readable, so turning the internet in a giant database, basically. And in 2006, published a note, a design note about his semantic web project, where the linked data concept, the term, was coined. So that's how it started. Linked data has been around since 2006, and it's heavily based on web technologies, right? So how it's going. So in 2007, a year after the notion was introduced, there were only 12 linked data sets. And by 2017, the number of them came over 1,000. So you can see an evolution of the number of interlinked data sets. Nowadays, people are talking about linked data a bit less, and it is connected with the emergence of transformers. You may have heard about them in the context of large language models or AI. So since 2019, NLP engineers have become better and better in working with unstructured data. So the push to make the data structured isn't as strong now. However, it is still very important because large language models that are behind every AI system don't have any inherent fact-checking mechanisms. And a lot of AI agents and systems employ knowledge graphs to check the information, right? And knowledge graphs are essentially based on linked data. So it is a very important technology, although it's not a buzzword anymore, right? You won't hear as much of it now. It's still a super useful thing. So now the number of data sets listed in the linked data cloud, linked open data cloud, is 1,354 as of March this year, the latest the database release, the latest release. This website, Link Open Data Cloud, is managed by several universities, including the University of Galway. And I'd say we now have a leading role in that. So in this visualization, I'll probably show you. You can click on, see, yeah. This is interactive, right? These are all the linked data sets that are available, and they're separated by different domains, general domain, geography, linguistics. Let's have a look at linguistics. So this is clickable, and you can't see what I'm choosing now, but whatever it, come on, what is it? Oh, I don't know. It's probably some internet problem. Let's do it again. Try and do it again. So what should happen? You should get some information about a data set and the link to download it in different formats. Yeah, I don't know.
Seems offline from the
Yeah, okay. Anyway, so that's what should happen. And I just wanted to show you this resource straight away because it's very valuable if you are looking for a linked data set. Okay, let's go back to the slides. Okay. So a few important data sets of linked data are, first of all, DBpedia and Wikidata, which are both community-based efforts to extract structured data from Wikipedia. Just Wikidata is managed by Wikimedia Foundation, and DBpedia is a different initiative. DBpedia is it contains 9.5 billion structured pieces of information, and these structured pieces of information or statements are called triples. We'll talk about this notion a bit later in more detail. Wikidata is even bigger now, and these are general purpose, general domain knowledge bases. And apart from that, there are a lot more specific data sets like GeoNames that has a huge linked open data database of geographical names. Europeana that has metadata about cultural heritage, text, images, videos, sounds, converted into linked data format. And a lot of government data sets across different countries, across the European Union, UK, Ireland, the US, can be accessed, can be downloaded in linked data format. This will be something about health data or income, so all sorts of government data. Okay, so what makes linked data special? What makes it different from any other kind of structured and unstructured data? So Tim Berners-Lee introduced the design principles of linked open data. Everything should be referred to with a uniform resource identifier, or URI. This is a unique pointer for an object or a relationship between objects. So everything is a URI. It might sound similar to a URL, and you'll be right in thinking so, because a URL is a type of URI. It stands for unified or uniform, resource locator. And there is still some debate in the community. Some people use these two terms interchangeably. Some people still use URL as a subset of URI, but URI is like a general term. Then the second design principle is that HTTP URIs should be used so that people can look up these names. So they have to be accessible through the web. When someone looks up a URI, some useful information should be provided through open standards such as RDF, SPARQL, and so on. We'll talk about what these acronyms stand for in a minute. So the third principle is about standardization, right? And the fourth principle is that other things that are connected to an entity should also be referred with their URI-based names. So the idea is, given everything in your model of the information, a unique address, a unique identifier, to avoid any ambiguities and to ensure discoverability. Okay. He also introduced the 5-star linked open data framework. You'll have the link to where all of it is described. It's from 2006, but it's still valid. So it measures how good your linked open data, or just data that you want to publish is. So it's just, the first step is just to make the data available under an open license on the web, right? The next step is to make it not just available, but to make it machine readable. For example, if you have a scan of your of a manuscript, if you just publish the scan, it will be just 1 star. If you make it machine readable, for example, if you extract text from it and make OCR results available together with the image, it brings you to step 2. Then step 3 is use a non-proprietary format. For example, if we're talking about tables, CSV is more open than Excel, because Excel is a proprietary Microsoft format, although there are alternatives that can open Excel files now. But still, it was from 2006. So number 4 is using open standards that are governed by worldwide, I keep calling it wild, World Wide Web Consortium, like RDF, to identify things. So standardization is point 4, and the point 5, the highest step, is link your data to other people's data to provide context to enhance discoverability. So these are the 5 principles. But what, how is it structured? How does linked data look like? So first of all, let's go back to that uniform resource identifier thing and see what it is. So the formal definition is a compact sequence of characters that identifies an abstract or physical resource. So just a sequence of characters, a unique sequence of characters that points to something, be it an object in a real world or a concept. And it is quite a broad notion, so all of these examples are valid URIs. So it's not necessarily a web address as we see it most often, like something with HTTP. It can be an FTP server, like for file transfer, it can be an address to a file. It can be an address to like a link to a page. It can be an email address with the mail to protocol. It can be an address in your local system, can be a telephone number, as long as it follows a specific format, the protocol first, and then the or schema, like protocol schema first, and then your unique identifier. But we mostly deal with these kind of URIs when we work with linked data, and they are called HTTP URIs because they use HTTP protocol. So the scheme here is a description of the type of the URI and the associated protocol. There is a list of registered schemes. It's quite long. I'll probably add a link here. When I'll share the slides with you. Then the next part of a URI is called an authority. It is a host name, like a website name, and optionally a port. The port is this, something after the colon. We won't go into details what it is right now. So this is called an authority. Then we have a path, and a path is the reference to the content on the host server, and it is in a way the same as your file tree on your computer. So you can think about it as folders that are nested, right? So animals is a top folder, and then inside it you have a folder domestic. So it's a hierarchy. And then after the path, you can have optional bits. So everything up to the path is obligatory, except of the port, right? So you have to have the scheme, authority, and path. But then in HTTP URIs, you can have optional query. It's everything that comes after the question mark sign. And here, for example, we have a query, and we ask for a variable called name, and it has to be called cat. And then we can have a fragment. A fragment is everything that comes after a hash symbol. And here it's paw as an example. So this unique HTTP URI points to a cat paw object. Okay. Right. Now, more acronyms. So RDF was mentioned before. RDF stands for Resource Description Framework, and it is a standard by W3C, and it is used to describe and exchange linked data. In RDF, pieces of information or RDF statements are represented as triples, and these triples consist of a subject, an object, and a predicate. A predicate is a directed link from a subject to object that defines their relationship. We'll see an example in the next slide. To describe this, there are different ontology languages. The most prominent ones are RDF schema or RDFS and Web Ontology Language or OWL. These are just the syntax that is used to describe these things, right? And they are all managed by the W3C. So you'll find descriptions of them on their website. And again, there will be links to it in the slides. Then, so you have triples, these individual pieces of information. And then to organize your data in the model, where all these entities that can be subjects or objects, they are properties, so the whole list of relationships between them, and data properties as well. A model where all this is described is called an ontology. So you'll hear this word a lot when you deal with linked data. And then finally, a collection of triples or a collection of RDF statements is called a knowledge graph. Okay, so here is an example of what RDF triples are. So this is an example about a writer called Margaret Lawrence. So we can say that Margaret Lawrence was born in Canada, and Margaret Lawrence is an entity, or and she is a subject in this particular statement. She was born in is a predicate, and it defines a relationship between Margaret Lawrence and Canada. Canada in this statement is an object, right? Another statement is Stone Angel, is her novel, I think, if I remember correctly. The predicate is set in, and Manitoba is an object. So if you ever came across formal semantics or formal logic, it may sound familiar, it may look familiar, that everything can be described as a set of facts, and these facts consist of subject, object, and predicate. Okay? That's the pillar of linked data. That's how everything is described. To make the model a bit more complicated and see how it uses the idea of connecting different resources, different websites, can have a look at this scheme. And here we have two persons that work in different organizations, and each organization has a page for their employees. So this person, Frank, works in some organization called acme.com, and he has a page with this link, and it is his identifier, right? He knows Victoria, who works in another company, and she also has a page in this company. That's her unique identifier. Separately, we can have different statements about them. For example, that Frank knows Victoria, Frank's date of birth is this, and his birthplace is that. Same about Victoria. And also, with something like geographical locations, we can link them to another website, another data set, right? That will have the coordinates and other information about these websites. So we know that Victoria's birthplace is in London, and we can connect it to another website, GeoNames, that I mentioned before, and see what information about London it has. So it is a way to pull information from different places following the links. Okay. SPARQL, another thing that was mentioned before, is a way to get this information, to follow the links and pull the information from the resources. It stands for SPARQL Protocol and RDF Query Language, and it is in a way similar to SQL. So it allows for a query to consist of triple patterns, conjunctions, disjunctions, and optional patterns. So all these, again, statements, as you may know from formal logic or programming, and or not, this can be used here. So, and many linked open data datasets and repositories have a SPARQL endpoint where you can query the data there. For example, Wikidata has a query endpoint. Let's see if my internet works now. Okay. So we won't go into detail about the syntax of SPARQL. It's another huge subject, but I'll just show you what you can do. We'll just use one of the example queries. Oh, this query called cats. So it says select all items and their labels, so their names in human language, where the type of this item, when you hover over, I can't see where my mouse is, mouse. here. Yeah, you can see what it stands for, because in Wikidata in particular, all the entities and relationships are coded with this letter number codes. So you can see what it stands for. So where item is of the type cat, domestic cat. And the statement just tells you in which language to display the labels, because Wikidata, as Wikipedia, is multilingual. So if we run this query, we will see all the entities in Wikidata that are cats, domestic cats. And if we open one of them, let's open it in the same tab, we will see all the information about this entity. So we can see the labels in different languages, for example, English and French, the label in Irish. Wikidata, as Wikipedia, is community edited, so you can contribute. And you can see the statements, or RDF triple. So this unsinkable Sam is an instance of a house cat. That's how we found it. And it is an individual of Felis catus. We also have an image associated with it. What is it? Allegiance. Oh, didn't know that. Okay, so all the different properties, and all of them can be extracted, right, as triples. Well, they are structured as triples. We're just looking at them in a more human readable way. Okay. Oh, unthinkable Sam. My God, I hate this top thing. Because I can't go to the tab I want to. Yeah. Okay. The queries can be, this is a very simple query. You can create, I'll just put it here, a more complicated query. For example, here we have an example of cats with pictures. And you can see that it selects, apart from the item label, it also selects an image. And if we run it, you'll get all the cat pictures on Wikidata. Which is nice. And a very important feature is that you can download your results in JSON or CSV or TSV format. TSV is like CSV, but the separators are tabs instead of commas. So it's very handy if you're looking for some data. You can just query Wikidata or Wikipedia or a large knowledge base, download the results, and then say analyze them or visualize them. You can also download the code for it. For example, this Python. And you'll have the code to get this data from this resource in Python. So if you copy that and run it, you'll get the results. So it basically does everything for you, which is nice. And they also have a nice thing called Query Builder, which is, if you don't know SPARQL, you can just start typing the name of a property, like is, say, instance of, matching without or regardless of value. Matching means we are looking for something that is an instance of, without is the opposite. Regardless of value, it doesn't matter, right? And here we can, again, in human language, type something. Cats. No, house cat. So yeah, we're looking for everything that is an instance of a house cat. Run query, and we must get the same results. Did I press it? Can't see my cursor. Okay, just imagine I pressed it. We'll go back to the presentation now. Anyway, it's just one of the data sets, one of the biggest data sets that is very useful, whether you know SPARQL or whether you don't. Yeah, now we can go back to the slides. Yeah, these are just the results of cats with pictures that we already saw and the download. Okay, but how do we store these collections of linked data? They're usually recorded in either text-based or XML-based formats. Text-based are N-triples and Turtle that is evolved from N-triples, and XML-based, the most popular one is RDF/XML. This is what you will see inside of a linked data file. If you download linked data, right, and open the file in a text editor, this is what you will see. Regardless of the syntax, regardless of the format, it will have prefixes first linking to vocabularies. So everything is unique, everything has an address, every relationship, every type of an object, right? So you don't have to create everything from scratch. You can refer to vocabularies that already exist. In the presentation, I will give you a set of common vocabularies or namespaces, they're also called. So for example, here we're using RDF on the left, RDF namespace or vocabulary, Dublin core, and something else. So first you define them, not to write this full link every time, and then you can just use relative path instead of absolute path by saying RDF something instead of the full link. And then you define all entities and all properties. Right, RDF XML is basically the same. The syntax is just a bit different, but in the same way, the first thing is a list of prefixes, and then you just define everything in your ontology, every class, every individual, every relationship. We'll see what these means, classes, entities, relationships, in practice, working with Protégé in a minute. So what is Protégé? It is an open source tool, an open source ontology editor by Stanford, developed by Stanford. You can download it, you can use a web version. It of course has documentation and a wiki that links to some tutorials. For example, the pizza ontology tutorial. So what we are going to be working with today is the pizza ontology. It's probably the most popular one in Protégé tutorials. It just describes different kinds of pizza to introduce you to the hierarchy. That's the link for the ontology, but if you downloaded Protégé, you don't need to copy this link because it is listed there as an example. Okay, so useful vocabularies, we don't need that now. And for the reading, you will just have it when I send you the slides. I'll probably just say a couple of things about this in case I forget to do it later. So the first two are the posts on the Programming Historian website. It is a great website with tutorials mainly for people in humanities who want to use digital tools. And they have one on the principles of linked data and another one on using SPARQL to access linked data. So I highly recommend this. The number 3, practical guide to building our ontologies using the latest version of Protégé. It is quite a big one. It's like 90 pages, but it is very detailed and it describes every view and every concept within Protégé. So if you really want to organize your data as an ontology, it is a good place to go. And then a couple of other tutorials in different formats, like some slides and a post on Medium for if you just prefer information in a different format. the number 6 is linked to the original linked data design principles. And the last one is the World Wide Web Consortium. Linked data. So where they have all the descriptions of RDF and turtle and owl and everything. Okay, now what we are going to do is open Protégé. Has everyone downloaded it? Okay. Opening, I hope. Okay. So I'll just maybe change my sharing settings to see what is on the screen. Sorry, not sharing settings, display settings, I meant. Okay, so that's what Protégé looks like when you open it. And you can create your own ontology from scratch. But what we are going to do is open from URL. And here are some examples, including the pizza ontology. So just choose this one and click OK. And it is going to import it for us. So this is the main screen of Protégé that has some ontology level metadata. So you can think of an ontology as a data set. Okay, so it has a title, it has information about people who contributed to it, it has a short description. And then we want to talk about axioms today because it's probably a bit too much. We will now go to the next tab that is called entities. And entities are classes, properties, data types, and individuals. So we'll go through all of them one by one. So everything in the class type is a subset of the thing. So every object or subject is an entity, is a class, right? And it is a subclass of the thing. So here we have the main things, we have countries, and we have food. So countries here have some, like every entity, every class has an annotation. It has labels. It can have labels in different languages. Here, for example, it has a label country and pays in English and French. And it has a comment, short description. Then there are statements about this in linked data format. So first of all, this statement equivalent to, it is self-explanatory, I think. It just says a country is a domain thing and one of these individual instances, individual objects, America, England, France, Germany, Italy, that we have described in this ontology. And you can see them listed under the instances menu. Now, if we go to food and then open the hierarchy here, we have ice cream, pizza, pizza base, pizza topping, and pizza, so we can see the some other relationship, subclass of. So pizza is a type of food in the language of formal logic and the language of Protégé. It is called subclass of food, and it has to have some pizza base, right? So it's not, it's narrowing down the definition. Okay. So we can edit all this. So if we press the cross, it deletes whatever statement there is. If we press this little circle, it means edit. And we can also add instances. Now, another interesting thing here is just disjoint with. It means that if something is a pizza, it cannot be an ice cream at the same time, right? And usually the objects on the same level of the hierarchy, so here we see food types, ice cream, pizza, pizza base, and pizza topping, are disjoint. So it means if it is one of them, it can be another. Okay. Now, within the pizza class, we have different types of pizzas. And they are described in this formal logic language. So a cheese pizza is something that is a pizza and it has topping that is an instance of cheese topping. So if we go to pizza topping here, we have a cheese topping class, and it can have different individuals at this, so cheese and vegetables, 4 cheeses, goat's cheese. So for pizza to classify as a cheese pizza, it has to have some of these toppings, right? Any of cheese toppings. So that's how we define it. And it has some pizza base. It can't just be a topping, right? It has to have a base. So I hope it makes sense, the logic in which everything is described. Does it make sense? Okay. Okay, then we can probably go to object properties. And again, as old thing was the top for classes, our top object property is the parent class for every object property. Object properties are our predicates that define the relationships between subjects and objects. So, for example, we can say that some pizza has some country of origin. So if we go back to classes and there is, which one has, don't remember, some of them must have a country of origin already encoded, but say, I don't know, spicy pizza has a country of origin, Italy. It is something that describes our data. Another one is has ingredient, and important things about properties. They have some, they can be of different types, right? They can be functional, it means, well, just they describe, they can have like subject and object. It can be transitive, it means that if an object A has a property B, or has a property that is an object B, and then an object B has a property that is an object C, that like this A to B and B to C relationship translates to A to C. It's easier to draw. I should probably have included some graphs. I'll probably do it in the slides. Anyway, symmetric and asymmetric, I think it's self-explanatory. And reflexive is when an object is described by a property, and it is both a subject and an object, right? So kind of a loop. Now, properties can, as classes, be equivalent to, so they can be described in different ways that are equivalent. They can be sub-properties of a different property. They can be inverse of a property. So if something has ingredient, for example, pizza has ingredient cheese, it can be inverse of a property is ingredient of. So if pizza has ingredient cheese, then cheese is ingredient of pizza. Okay? Domains describe subjects, so everything that is on the left of this arrow. So whatever is on the left, whatever is the subject, is ingredient of ingredient of property is food. And in this case, whatever is an object is food too, right? So ranges, they describe objects. For example, we can make it more specific and say, well, if we just describe pizzas and don't have food at all, we can say that the domain of this is pizza toppings, and is ingredient of, the domain is pizza toppings, and the range is pizzas. So every pizza topping is ingredient of some pizza. Okay, if we narrow it down. Okay, it's all needed. All these statements are needed so that we can automatically infer other statements about the data, right? So all these transitivity and reflexivity, and if properties are symmetric or not, is important for automatic reasoners, and we'll see it in a moment. Okay, apart from object properties that regulate the or describe the relationships between subjects and objects, between classes or individuals, there are data properties. Don't have anything here. But we have annotation properties and data types. So annotation properties is everything that describes our entities in the human language. So we have title, we have description, we have label, these things that were in this top right pane here. Then we have data types. So for example, we can if we describe someone's date of birth, or if we describe coordinates, we can restrict which data types we can use for an object. For example, a date of birth can only be of the type date. And all these data types are already described in different vocabularies like RDF or OWL. You don't have to define these things yourself, right? So like all the data types like integers or dates or different formats of dates are already there, right? And if you can restrict them if you need. And then you have individuals. Individuals are representatives of a class. For example, we had this class country, and individuals that we have described in our ontology are England, France, Germany, and Italy. And we can add another individual, say Ireland, right? And it appears here. And if we go back to classes and go to country, we will see. Oh, we won't see it, but we'll see it when we run a reasoner. So what is reasoner? If you go to reasoner and select hermit, there are different types of them, but this is a pretty good one. And then you click run start reasoner. It will infer some statements that you didn't put in your ontology manually. And they will be highlighted in yellow. It's weird that it didn't infer Ireland here. Because it should have. We added Ireland as a country, as an individual of a country class. So it should have. Okay, it's because this statement is restrictive. So should add it here.
Why doesn't it work as it's supposed to? Okay. I'll have a look into it. It should have appeared here, maybe.
Some other section.
Probably should be. Anyway, I'll have a look into it. Won't lose time on it now. But anyway, you can see the things that are inferred by an automatic reasoner highlighted in yellow. For example, if we have this pizza called real Italian pizza. We defined ourselves that it is a pizza. It has country of origin Italy. Its base can only be thin and crispy, not any other base. So the reasoner inferred that if the has base property can only be an instance of a thin and crispy base, then it is a subclass of thin and crispy pizza. Okay, so it is recreating these missing steps, logical steps in our ontology, and enriching the description. So it can be very helpful because when you are creating your own ontology, you can just add the basics of the hierarchy and let the reasoner do the job and infer other things. Of course, it can be wrong, and you have to double check it, but it is quite a powerful tool. Okay. Now, what we can try is, as an exercise, is to add another pizza. So we already added a country of origin, a new country of origin, Ireland. We can create, I don't know, an Irish pizza. You can imagine yourself what it can be. And what kind of pizza it can be. Is it cheesy pizza, a meaty pizza, or something else? And add this new class in the relevant part of a hierarchy and define it. For example, you want to add some new topping, I don't know, potato topping. You have to create this topping first, right? And then define an Irish pizza as a pizza that has, for example, thin and crispy base or any base and a potato topping, or a potato topping and a cheese topping. So construct your own pizza and define it in the ontology. So this will be the task while I try and find a charger for my laptop that I forgot. Okay. Yes. Hey, how's it going? It's working for you? You can try and do it together. So I already added a new country here. Okay, just add instance. Okay, have to add. Yeah, okay, I see. We added Ireland to the list of individuals, but we didn't add a statement that it is an instance of a country. So that's why it didn't appear there, it seems. Okay, let's see if, yes, it is here now. So we added a new instance to the class country. Okay, let's create a new pizza topping. Let's first see how the toppings are defined. So there are cheesy toppings, subclass of pizza topping, subclass of vegetarian topping inferred. Okay, and we don't have any instances, it's just a class. For cheeses topping, it's a cheese topping and it isn't spicy. Again, these properties are not obligatory, right? So you don't have to define if a cheese topping is spicy or not. But it adds additional information to your data. Okay, ghost cheese topping, mozzarella, right? How their toppings are structured. It's a pizza topping, meat topping. Yeah, we don't have any deeper levels in the hierarchy, defining some meats, not to overcomplicate it. So let's just create a new topping called potato topping. Okay. So I haven't explained these things. If you choose a class and then these are buttons that let you to add a subclass, add a sibling, which means it will be at the same level of the hierarchy, delete selected class, or it's called a selection. So say we choose pizza topping and we want to create a subclass, a new subclass of pizza topping called potato topping. And it automatically, I mistyped it, automatically creates a unique URI. It's called an IRI here. It's an updated version of a URI, and it stands for Internationalized Resource Identifier, and it allows for non-ASCII characters, as far as I remember. So it is suitable for different languages. Okay, and we click OK. So we can see that potato topping is here. We can right-click on this and select Make Primitive Siblings Disjoint, which means that if pizza has a potato topping, it cannot have fruit topping or meat topping. But it's probably not something that we want. We probably want potato topping to be combined with some other toppings, so we don't want to do that. We will use it in another level of hierarchy. Okay, so we have potato topping, and it is a subclass of pizza topping. Good. No more different subclasses of it. It's not as sophisticated as cheese. Okay, actually, we may say that it is a type of vegetarian topping, like these for ones. We didn't put it here, but if we add a statement, it should move, I think. Subclass of. Should do it here. Come on. Make it a vegetable topping. Okay. Now we create a new topping, and now we want to create a new pizza. So named pizza, spicy pizza. Let's just create it at the same level as all of these. So again, we can create a subclass of pizza and call it Irish pizza. And in this instance, we want to make it disjoint with every other pizza. So make primitive siblings disjoint. Okay, so it's disjoint now with unclosed pizza, named pizza. Great. Now we want to provide a more detailed definition of what it is. It's not just a pizza. It is a pizza that has potato topping and maybe something else. So let's see how other pizzas are defined to see how we can define a new one. So, for example, cheesy pizza is pizza and has topping, some cheese topping. Meaty pizza is pizza and has topping, some meat topping. Named pizza. Maybe we should have put our Irish pizza here. Named pizza, American, has country of origin, value, America, has topping only mozzarella or pepperoni or tomato, has topping, and is a named pizza. Okay, so probably we want to move this in a named pizza. And we can just drag it, and you can see that the description here changed from subclass pizza to subclass of named pizza. Let's see again how the American one is defined. Let's add statements one by one. Has country of origin, Ireland, and has topping, potato topping. We want to restrict it to only. There are different ways to do that. You can choose from class hierarchy, or you can create an expression, or you can create a restriction, as I mentioned before, of the data type that it can be. It's not our case. So we will just say has topping value. Value means the topping has to be this particular class or entity. Potato topping. Have I typed it right? Potato topping. The individual name. Okay, values can be only individuals. Okay, then some potato topping. Fair enough. But then we can have a has country. If you press tab, it will autocomplete with the name for you. So it has country of origin, and here we can use value Ireland, because Ireland is an individual. So yeah, what was I doing? I was writing a statement about, I can't click on it. Statement that an Irish pizza is pizza and has country of origin value Ireland. So something like that. Okay. And of course you can save your changes and you can export the ontology in different formats. So if you go to File, Save As, you will have these options like RDF XML or Trail or all XML and a lot of different varieties of all or JSON optimized for linked data. Another option, especially if you say want to visualize your ontology in software like Gephi or in any Python library, it might be easier to work with CSVs, although there are plugins that, for Gephi, for example, that allow to import RDF formatted data. So there is a plugin called Export to CSV, and it is under Tools. If you don't have it by default, so I don't remember if I installed it or not, you can just go to check for plugins and install this plugin. But anyway, if you do that, you can, of course, choose where to export the file. Let's see, okay, somewhere in the documents, you can choose the entities, and that's a visual selector, right? You don't have to export everything. You can choose the entities. For example, to visualize your ontology, you may not need some properties, some metadata like descriptions or titles or language labels or data types. You may just want the objects, different classes and individuals, and the relationships between them or properties, right? So you can just choose these individuals, object properties, and entities, right? And you can also export value of properties. We probably only want the value of properties that are object properties because we don't want our data types to show in the graph, right? So you can select all this. You can select your delimiters, include headers, and include column with entity types, for example. So all sorts of settings, and click OK, and you will get it in your CSV format. Okay. So this is basically all the theory I wanted to share. So my idea was that we will try and add more different kinds of pizzas and toppings and play with the descriptions and run in the reasoner. For example, we added this new Irish pizza, so we can run the reasoner again. Oh, it actually is running in the background. So stop reasoner, start reasoner. Okay. Somehow it's equivalent to all, nothing. It shouldn't be equivalent to all, nothing. Interesting. We can click on the question mark sign if we don't know how the reasoner arrived at this conclusion and show the logic. Irish pizza is a subclass of named pizza, and disjoint classes are Irish pizza, named pizza, unclosed pizza. It is a bit weird, so we probably don't want this sentence, this statement. I didn't arrive at anything else. Speaking of graphs, I remembered that I wanted to show you something else in Protégé. It has some visualization capabilities. There are different plugins that are pre-installed, and you can choose in window tabs which ones are shown. So for visualization, there is Always and Ontograph. Always never works properly for me, so I prefer Ontograph. If it's not checked, you can just check it, and it's dynamic, and you can choose whatever item in the hierarchy. For example, I'll clear it first. Whatever item in the hierarchy you want to show, for example, pizza, and it shows you the top entity. If you click a plus sign, it will show the children in the form of a graph, and all the links it has. So when you hover over, you see the type of a relationship. So these arrows are actually different relationships. So these ones are subclasses. So pizza has subclass real Italian pizza, interesting pizza, named pizza, right? And this named pizza has subclasses. So you can see this hierarchy. Then there are different types of links. Pizza has base, and pizza, what is it? Another one. Pizza has base, subclass, some pizza base, and translates the main range. Okay, yeah, so pizza has a property that it has some pizza base, and then they are connected with the domain range relationship. So pizza is a domain and pizza base is range. So and then pizza is a subclass of food. So you can just click on these things and expand the relations connected to each, describing each node. When you hover over, you can see all the statements and the URI. For example, it's very small, the URI for interest in pizza, the equivalent classes, the definitions of equivalent classes, and annotations like labels and descriptions. You can choose different layouts here. So horizontal, from left to right. And you can save this graph as a picture to insert in your work, a paper, save current graph. So, well, you can serve it as an ontograph file, right? And you can also save it as a picture, which is the camera item. Export graph as image. Right. PNG, JPEG, or GIF. Okay. So this is not probably as nice as the visualizations you will get in Gephi, but when you're working with your ontology for a description of your data set, it's helpful to see the hierarchy and the types of classes and properties that you have.